So today we're going to be learning the transformations of graphs and how they affect the function and its equation. So we're going to start with translations. So translations are basically shifting the graph as it is somewhere on the xy plane. So if I had this xy plane, and let's say I had a function y is equal to f of x is equal to x square. And now let's say, so anything like shifting a function, the same function, just shifting it up or shifting it sideways would count as a translation. Let this be and this. We know that the blue graph over here is x squared. And now we want to find the equation of these two graphs. So let's look at the vertical translation first. And so we would want to shift this graph of y is equal to x squared up by 2 units. And a translation will always have an equal shift at every corresponding point. So this distance from this point over here to its corresponding point on this graph would be equal to this distance of this corresponding point over here at this graph, and such that for all each and every point on both the graphs. So when we do this vertical translation, what we are doing is we're pushing this blue parabola up by 2 units. So how do I express that in terms of this function? Let's see. Let's just think about it. The output in this case, which is y, is basically getting added by 2. So let's say if I had 0 over here, this is 0 plus 2, right? And if this was 1, I would correspond to 1 over here, because 1 square is 1, and that corresponds to 3 over here. And if this was 2, it would correspond to 4. When it would transfer to here, it would correspond to 6. If you notice, what you're doing is that you're adding all the outputs of this blue function by 2. So in that case, this green function should be x squared, which is all the outputs of this, plus 2. And if you notice, if I put 0 here, I'll get 2. If I put 1 here, I'll get 3. This is the same thing that's supposed to be happening for the green function. So for a vertical translation, okay, if I'm moving upwards in the positive direction, the changed function would be the original function plus the factor of the translation. So if I'm translating it, if I'm doing a vertical translation of a factor of a, then I'd be moving it up by a units, and so this would be the function. And if I was moving it down, then it would be a vertical translation of the factor minus a, and that would be f of x minus a. And this can also be written as a translation with a factor 0a, or a translation factor 0 minus a. And in that case, I would move it either up or down by a units. Now let's look at the horizontal translation. So if you notice, what we're doing here is that we've moved this blue parabola 3 units to the left. So when I input minus 3, I would want its output to be 0. And when I input minus 2, I would want its output to be, in this case, 1, right? Which would be if I had inputted 1 in the blue function. So if you notice, what we're doing is that we're adding the input by 3. So when we want to move it to the left, I'm just going to write it over here. It should be, we want to add the inputs by 3 and then go through the function. And so we get x plus 3 squared. So if you input minus 3, you would get 0. If you would input minus 2, you would get 1. And so if you notice, when we move to the left, we're adding by 3. And so if we're moving to the left, the new function would be the old function within it. Within it, we would minus it by a if we were moving to the left by a units. And if we were moving to the right, we would add it by a. And if we were moving to the right, we would subtract it by a. If we were moving to the right by a units. And again, this can be written as a translation with factor either a0 for the second case instead, because you're moving it a units to the right, right? That's when you'd subtract a, but you would still write it as a translation of a0. And when we're moving to the, this is for the right. And when we're moving to the left by a units, we could write it as a translation with a factor of minus a0. Another very important transformation is a stretch. So, as you know, a stretch would be to kind of pull something and deform it in a certain direction. And that's exactly what we do with a function. So, now we're just going to look at. So, we don't want a symmetrical function. And although y'all haven't learned what sine x or cos, the functions of cos x is, I'm just going to use one of them because these are very easy to explain stretches with. And just for now, I'm just going to tell you that the graph of sine x is this. But this isn't important to you right now. It will be important when we're doing when we're doing trigonometry. So for now, just assume that we have this function. And now let's say, so this, something like this, would look like a vertical stretch. And the blue one, which is y is equal to f of x, is a horizontal stretch. And the green one, which is y is equal to g of x, is a vertical stretch. And the red one is y is equal to sine x. And let's say that's h of x. Okay? So now we can stretch these as a factor of twice or thrice of it. And what it basically means is, so okay, a vertical stretch basically means that, so let's say this is at, this value over here is 1. So if I stretch it by a factor of 2, at every point its y value will get multiplied by that factor, and thus it'll move up or down depending on if the factor which I'm multiplying it with is greater or lesser than 1. So let's say I stretched it right now by a factor of 2. So every point on this red graph should get multiplied by 2, every output value. And so it stretches up in this case, and this upper value should be 2. Okay? And like I just said, every output value would get multiplied by 2. And hence, we would make this 2 sine x. And if I had to half every output value, then it would come down because every output value would become lesser than what it is. And so it would be something like sine x upon 2. So now for vertical stretches, if you want a vertical stretch, and if the original function is h of x, you would make it a vertical stretch by factor a. You would make it a times f(x). So now that could be 1 upon 5, or that could be 5. And what you are basically doing is multiplying each output value by that number. And now in this case, we have elongated it in a way. And what we are doing is basically, for each of these input values, what I have done is I have halved the input values. If I have doubled this, which I have, I have halved the input values. And so let's say this input value is 90 degrees, as we know that sine of 90 degrees is 1. Okay, and so if so now let's say while inputting it into this blue function, I inputted 90 degrees, but then I halved it. So I would get something like 45, which would be lesser than 1. And then only when I inputted 180 degrees would the half of it be 90. So if you notice, when I half it, it seems to stretch out by a factor of 2, right? So this should be equal to sine x upon 2. And thus, for a horizontal stretch by factor a, so if I want to stretch h of x by factor a, I would have to make it x upon a. right? Because like I said, when I input it, I would get it would divide by 2 and then actually be inputted. So it would take longer for the function to reach a certain value, and so it tends to stretch out like that. While in this case, I'm just simply multiplying each output value by a certain factor. The third transformation that we will be doing is a reflection. So there are two kinds of reflection that we will need to know for the IB, and one is a reflection in the y-axis, and the second is a reflection on the x-axis. So now for the reflection on the y-axis, let's say I have this function, and I want to reflect this along the y-axis. So the reflected version of it should look something like that, right? If you notice, what we're doing during this reflection along the y-axis is that we're keeping all the y values or the outputs the same, as if you notice that these outputs like are the same as these, except it kind of looks shifted or something. But for every positive value over here, we're making it negative, and for every negative value over here, we're making it positive. That means that we're changing the sign of the inputs. So when we're reflecting along the y-axis, we would be changing the sign of the input. So we make it minus x. So it become f of minus x. This, if h of x was a reflection of f of x, where this is f of x, then this h of x, this green colored h of x, would be equal to f of minus x. Because if you notice that when I input these positive values, like let's say this is 3, I will get minus 3 is equal to that same y value. 4, then minus 4 would be equal to that same y value. Yeah. So reflection on the x-axis. If I had a function that was something like this, and I wanted to reflect it in the x-axis, the result would be something like that. And now if you notice that for all the positive outputs, like let this be y is equal to f of x, and this is y is equal to h of x. So for all the positive outputs, I am actually getting a negative output. Like if this was 2, then this would be minus 2, and if this was 1, then this would be minus 1 at the same place. So what I'm basically doing is changing the sign of the outputs, and in that case it would, and hence it would become negative f of x, because what I'm doing is changing the sign of the outputs. So for a reflection along the y-axis, so now we're going to do consecutive transformations. And one thing we need to keep in mind in consecutive transformations is that a horizontal transformation followed by a vertical, and a vertical followed by a horizontal, either way, it doesn't make a difference which order I do it in. But if I do two horizontal transformations, it does make a difference in what order I do it in. So when we're given a transformation, we need to, in a way, backtrack. So given any transformation, we can always divide it into the order of the vertical transformations, and then we can look at the order of the horizontal transformations, as those can be interchanged, but the order of those vertical and those horizontal transformations cannot. Now, one way of looking at, or one way of trying to separate them is, yeah. So, vertical transformations, in a way, do follow the normal operations of mathematics. So, for a vertical transformation y is equal to f of x, I would, let's say I want to stretch it vertically by a factor a, and then move it vertically by move it vertically by a translation factor. If I did the translation first, I would get f of x times a, and then I would move it and it would become d. And if I did the translation first and then stretched it, I would get f of x plus d times a. And so I would get a times f of x plus dA. Okay? So given a certain transformation, we need to backtrack it. So now let's say I had x square, 3x square plus 2. So I can either say that it was first stretched by a factor of 3 and then 2 was added to it. But what I can also do is say that it was first translated vertically by a factor 2 upon 3 and then stretched vertically by a factor 3. So there are two ways of writing it, but this does follow the normal order of mathematics, as you can see. However, horizontal functions don't do that in that case, because what we're doing is we're replacing the transformation, we're replacing x with the transformation. So now let's say I had a function f of x and I moved it again. I stretched it horizontally by a scalar factor of a, and I moved it uh, horizontally by a factor d again. So if I did the stretching first, I would get ax, f of ax, and then after which, so this is the stretch, horizontal change, it would be the horizontal translation. It would be f of x plus d in brackets, right? So this would be equal to f of x ax plus ad. Although although I did the stretching first, and the other way around, if I did if it was f of x and then I translated it, it would become f of x plus d and then stretch. I'm just gonna write st. So then it would become f of ax plus d. And this can be a little challenging to do. So I'm just gonna do maybe one or two examples of this. Yeah, so I'm gonna just do an example or two of these horizontal transformations because they can confuse you sometimes because they're not the usual, like they don't follow the usual mathematical order. So now let's say I had a function g of x, and I've been given the function g of x minus 3 upon 2, and I've supposing you've been given a graph of this, and the question asks you to draw a graph of this. So drawing it would be easy if you just knew the order of the transformations that have occurred to get that have occurred such that g of x becomes g of x minus 3 upon 2. So now again, I'll tell you that whenever you do a transformation, you're replacing x with a certain value and not multiplying or adding x. You're replacing it with x minus 3 or 2x plus something. So what I would do is take this 2 out, just so that it's easier to look at, and this just makes things more clearer to see. So a good way of solving a sum like this is to backtrack. So how would I get g of x from this? So now that I've written it in this form, I can say that if I translate it to the left, to the left by a factor of 3, I'd get x upon 2, and then uh, if I stretched it by half, I would get g of x because I would have to replace it with 2x, right? So I would get g of x. And now just go backwards. So this is stretch by 2, and to the left, translation to the left, by 3. And it's that simple. So just backtrack and you will get the right answer.